So we good to go?
Yeah.
Okay, so I guess I'll just quickly review what we did last time. So I think in part one, I talked about how there was like physical space, and that's in physical space, like the up and down spinor states are like opposites. But then there's like the spinor, or like the state space. I'm not sure what you call it. And in that space, up and down are at right angles, because we have this inner product rule where one cannot collapse on the other. And I think because of that, we ended up finding that states rotate with matrices that belong to SU2, which means the Hermitian is the inverse, and also the determinant is +1. Determinant equals +1. And then in part two, I talked about these, like, if we have like a vector like x, y, z, we can turn that into what's called a polyvector by taking a linear combination of the sigma matrices, and that gives us this 2x2 complex matrix. And we found that if we want to rotate the components, we use this transformation here. So it's like a double-sided SU2. I can't write SU2. And then it turns out if V is null, or like it has like length 0, then you can turn it into like a row and a column. And that means that the row will transform with U and the column will transform with U dagger. And then, so that's kind of like how we got to spinors last time. So this time I'm hoping to finish these two sections, which are Clifford Algebras, and then I'm going to talk about how spinors are members of what we call a minimal ideal in a Clifford algebra, which, unless you've taken an abstract algebra class, you've probably never heard of that before. Okay, so I guess I'll just start. So there's going to be two ways I approach Clifford algebras. One is going to be like the Dirac equation, which I think we covered in the book. And then the second way is just going to be like pure math. So if you find this way might be a little bit confusing if you're not up to speed on the book. So like you might, next 10 minutes might be a little bit confusing if you're not up to speed in Road to Reality. But hopefully the pure math version will help unconfuse you. So I guess with the Dirac equation, we start with Einstein's energy momentum relation from special relativity. Does this look familiar to people?
Mm-hmm.
Yeah.
Yeah. So I'm gonna kind of rewrite it like this. So basically, I've turned the P into like all the components, and I think I've done like some divisions by C. So you can kind of think of this as, it's a bit like how like the space-time interval, you have like the time component squared, and then you subtract all the space components squared, and that's kind of the same thing, except it's with the energy momentum vector instead, and the squared length is mc squared. So I think with the Dirac equation, or I guess it was the Klein-Gordon equation, people took this equation and they used the rules where I guess you send energy to this operator and you send momentum to this operator. And if you, so I'm actually, I still don't fully understand why those are true, but that's kind of what you do in a quantum class. And so if you put that into here and do that for x, y, and z, then you get this. I've factored out the I squared and h bar squared from every term here. And then I think I turn this I squared into a -1 and divide by h bar squared, and I get this. So have people seen this approach before to get the Klein-Gordon equation?
Yeah.
Does this look like kind of familiar?
Like
Yeah.
we had that in the Road
Yeah.
to Reality. Yeah.
Okay, so all you need to do to get the Klein-Gordon equation is just operate on a wave function. So that's when you get this. And I think you can also, like, it's common in special relativity to write CT as x0, x as x1, y is x2, and z is x3. So that's another way of writing it. And then this whole big operator here, we've seen it written as just a square, which is called the D'Alembert operator. So this is the Klein-Gordon equation. Now this is a moment where I maybe didn't do enough research, but there's some sort of problems with the Klein-Gordon equation, and I can't remember. I think like the probability density like doesn't work out or something. Like you can get like negative probability densities. I forget exactly what the problem is. If Joe was here, he could probably tell me. But Slava, do you remember that there was some sort of problem with the Klein-Gordon equation?
As I recall it seems that Penrose also just told us that there are some problems with the probability density for that equation.
Yeah, like I'm not going to go into it because it's like a derivation, but like if you Google like Klein-Gordon equation problems, you can find that like you can get some results that don't make sense. And I think it's largely because it's second order in t derivative. Like I think the Schrödinger equation is only first order in time, and that's why it works out fine. But basically, Dirac wanted to fix this equation by making it first order in t. So basically, this is like an operator that has the squared derivative of time. Dirac wanted to find the square root of this operator, so it was only first order in time. So I'm going to do that right now. So this is our D'Alembert operator. I'm going to use a slightly different notation just to make it save space. So like, this just means like the derivative of the zeroth component. This is the derivative of the first component, second component, third component. I don't think that notation's too hard. And basically, we want to take the square root of both sides. And to do that, we're basically going to assume it's a linear combination of these derivative operators with some gamma coefficients, gamma 0, 1, 2, 3. And we basically need to solve for the gammas. And that's going to lead to the Dirac equation. So we need to figure out what the gammas should be. Oops, yeah, okay, I wrote that in actual text, but yeah. Okay, so this is the D'Alembert operator, and it's going to be the square root of D'Alembert times the square root of D'Alembert. And again, the square root of the D'Alembert operator is going to be a linear combination of these derivative operators with the gamma coefficients. So this is a sum of 4 terms times a sum of 4 terms, which gives us 16 terms that I've written out here. Now I've tried to color code them. Basically the blue term here, so the blue term we want to be plus 1, because like this partial 0 by partial 0 has a plus 1 coefficient. We want these purple terms to be minus 1 here, and that's because these have minus 1 coefficients up here. And then we want everything else to go to 0. So we don't want cross terms like partial 1, partial 0, or like partial 3, partial 1. We want the off diagonals to go to 0. So basically, we kind of want the coefficients to look like the Minkowski metric here. So does that make sense?
Yeah, it seems like one of the possible solutions to me.
Yeah. Okay, so moving forward with this idea, so we want the blue term to be plus 1, gamma 0 times gamma 0. We want the purple terms to be minus 1, so gamma 1 squared, gamma 2 squared, and gamma 3 squared. And for the red terms to go to 0, one solution is that we just make them anti-commute, so gamma mu times gamma nu plus gamma nu times gamma mu equals 0. And what that basically means is like this term and it's sort of like this term up here are going to cancel each other out. And that happens like all across this diagonal here. So like this term and its mirror image over here are going to cancel out. So the blue and purples give us the diagonal terms we want, and then this anti-commuting property here will cause all the off-diagonal terms to go to 0. And we can basically summarize all of these with this equation here. So this is the anti-commutator. And basically the anti-commutator is going to be 2 times the Minkowski metric. So for example, if I have gamma 0 plus gamma 0, gamma 0, then that's going to be equal to 2 times plus 1, because this is the 0, 0 component here, which makes sense because like this just squares to plus 1, this just squares to plus 1, and so yeah, that's 1 plus 1 is obviously 2. Whereas if it was like gamma 2, gamma 3 plus gamma 3, gamma 2, that should be equal to 0, because it's, that's just the anti-commuting rule. So this boxed equation summarizes everything below here. And basically what Dirac did is he just figured that these gammas, because they anti-commute, they can't be ordinary numbers, so they have to be matrices. So I guess just through like trial and error or just like solving a bunch of equations, he found that these Dirac matrices satisfied this equation. Now these are kind of like hard to memorize, but there's a little trick. Basically gamma 0 is just, you have the identity here, and then you have the negative identity here. So that's one way to memorize it, it's like here. And then with the other ones, which are called the gamma i's, you have like the positive sigma I matrix here, and then its negative sigma I matrix here. So for example, with gamma 1, this is sigma 1 here, and then this is negative sigma 1. And like here for gamma 3, this is that's just the third. You could gamma sigma 3 or sigma z, and then this is just the negative gamma 3 there. Okay, so that's sort of like the traditional approach to the Dirac equation. And if you write it all, yeah, so like basically if we want to take the square root of this in the Klein-Gordon equation, I think you can kind of treat this as like a difference of squares. If you put a negative here and a negative here, you can view this as like a difference of squares you can factor. So basically we get the square root of the D'Alembert operator minus I MC over H bar, and then we have the square root of the D'Alembert operator plus I MC over H bar. So we basically factor the Klein-Gordon equation into like square roots almost. Now the square root of the D'Alembert operator, we can write it in Einstein notation to make it shorter, so that's like an implied summation over mu from 0 to 3. And then another way I think is called the Feynman slash notation. So whenever you have something slashed, like A slash basically just means you sum components of A with the gammas. So here this is a partial derivative slash, so it's the partial derivative summed with the gammas. And this is a part I was not sure about. Like, okay, yeah, and here I think I multiply by H bar, because this is the way you see it in textbooks a lot of the time. Now I wasn't really sure if both of these are like different versions of the Dirac equation, or if it's just this one. I'm a bit unclear about that. Does anyone want to help me and give me the answer, or do we not know?
In book we just have like 2 names for those, like Dirac and anti-Dirac equation.
Okay, so they're both kind of equations. They just have like yeah, one is a minus and one is a plus. Okay, so they're both like valid, I guess. Okay, did we just get someone join?
Yes,
okay.
infra joined, yeah.
Okay. Yeah, so that's basically the standard derivation of the Dirac equation, which if you've been following the book, you've probably seen something like that. Did anyone have any questions?
Penrose connects that with matter and antimatter.
Exactly.
Matter.
I was just about to ask that if it's related to the antimatter.
Yeah, so I'm maybe a bit more familiar with the math and less familiar with the physics here. I think with the Dirac equation, you can get two sets of solutions for psi, and like half of them end up being matter and half of them end up being antimatter. But I honestly am less familiar with that. This presentation is a bit more math focused and less physics focused. But yeah, like
that the negative energy solutions are going to correspond to antiparticles.
So negative energy solutions correspond to antiparticles.
Right.
Okay. Cool. Okay. And
I have Chris. Excuse me. One clarification. I jumped in the middle, so maybe you explain it. But how did we end up talking about the space-time and Minkowski here with the spinors? Because last time, and when we started this excursion to spinors, we kind of started from a standard model. So is there some bridge we should know?
So like, do you remember what slide you hopped in at?
Yeah, just before that.
Yeah, so
we have this Minkowski matrix.
Yeah, did you see this?
Yes.
Yeah, you did.
Yeah, I was here, yes.
Okay, so were you confused when the Minkowski metric popped up? Were you confused around here?
Yeah, like this. So I was just thinking, what is the bridge in this matter, because we kind of started from a standard model and spinors in that area, and now we're talking about relativity.
Right, yeah. So basically what I'm going to show, and I think maybe I just need the next slide. Yeah, because again, I'm totally changing gears. Because like with these presentations, what happens is with a lot of the sections, I'm starting somewhere that seems completely random, and then by the end we'll get to spinors. So it seems like I'm starting completely random here, but we are going to get to spinors. And I think, so with the Dirac equation, if you interpret it as matrices, 4x4 matrices, so this, if you add all the Dirac matrices together with the partial derivatives, you get this big ugly thing here. And then you kind of have to pretend that there's an identity in front of the MC, like the number 1, to get a 4x4 matrix. And basically, this is a 4-component thing that we call a spinor. So in physics classes, I don't think they really explain too much what a spinor is. They just say it's like a 4-component wave function. And I think like you basically have to solve for all of the psi components. And as someone mentioned, like the negative energy solutions correspond to antiparticles. So from a physics perspective, a spinor, this 4-component spinor, is just a solution to this matrix equation. But I feel like a lot of particle physics classes don't really go any farther than that. They just say, hey, it's a 4-component complex column, just kind of deal with it. So I think now, if anyone has any comments or questions, you can feel free to...
I just wanted to add to the answer to Mesocosmos that actually we have started from the relativistic equation, from the relativistic energy. And therefore Minkowski metric was encoded in there, and therefore you have the same signature in terms of the signs in Dirac equation, or Klein-Gordon equation actually. So that's where the Minkowski matrix enters the scene.
Yeah, like the whole thing we started with, like if you might be rusty on relativity, but the 4-momentum vector in relativity looks like this. You have energy over c. You divide by c to give energy momentum units, basically, but it's energy, momentum x, momentum y, momentum z. And then you use the standard rule in special relativity where you can, like, it depends on the sign convention. I'm using the positive time, negative space, but you could also flip that and make all these signs backwards. And then the length of this vector is mass times the speed of light, which you can square. And basically, if you say momentum equals 0, that leads to like your standard E equals mc squared. But like this is the more general version of it. And as Slava said, the Minkowski metric is kind of encoded in this because we're taking the length of a 4 vector here.
Oh, nice.
Okay, so now this talk is supposed to be on Clifford Algebras. So basically, another way, yeah, so, and I think I took this from Wikipedia. This is another way of writing the same equation where C and H bar are 1 in the natural units. But yeah, I don't think you could write it either way. These both look pretty messy to me and hard to understand. Now, I want to start talking about how you can sort of change your point of view with these Dirac matrices and start thinking in terms of Clifford algebras. So here's like a non-technical answer for what a Clifford algebra is. It's basically a vector space where we can square basis vectors to get +1 or -1, and then orthogonal basis vectors anti-commute. So if you remember like the sigmas, those all square to basically the positive identity, right? And they also anti-commute, so sigma I, sigma j equals negative sigma j, sigma I. And we sort of have a similar thing going on with the Dirac matrices, where the time one squares to +1. The space ones, I'm just going to write gamma I, square to -1, and then they all anti-commute with each other. I guess equals negative. So if this doesn't make sense yet, I'm hoping it'll make sense in about like 5 slides. But basically, the idea of squaring basis vectors and anti-commuting basis vectors is sort of the starting point for a Clifford algebra. So to make this a bit easier to understand, I'm going to go back to maybe what's a little more basic. So let's say that someone gives you I squared equals -1. And they might, say, hey, what's I? How do I solve for I here? So one option might be is to convince yourself that I and the number 1 are really matrices. So you could say, well, 1 is really the identity matrix. And then I is really this matrix here where we have a -1 and a 1 on the off-diagonal terms. And if I square this I matrix, I end up getting like a negative identity or like a -1. So like, if I do this multiplication, I think like 0, yeah, like this just becomes a -1 times a 1, so that's a -1. This ends up being 0, this ends up being 0, and then this is that times that, so that's also a -1. So that just gives you a negative identity. So you could convince yourself in this equation that, this is a matrix problem and I solved it using matrices. And you could say, well, A plus IB is really just this 2x2 matrix here, where like, the identity parts give you A, which is like the real part, and then the off diagonals give you the I, or imaginary part. So that's one way to look at it. But you're probably thinking like, oh, this is just complex numbers. So like the second option is to just, we don't really solve for I. We just treat it as like a definition. So we just say like, yeah, I is just a new number or a new symbol, and then I squared equals -1 is just the definition. And so this is sort of, we've basically invented our first Clifford algebra. So this is what we call the Clifford algebra 0, 1. Also called the complex numbers. So the 0 is counting how many symbols square to +1. So we don't have anything that squares to +1, so we say 0. And then the 1 is counting how many symbols square to -1. So we have I, so that's one symbol that squares to -1. So we say the complex numbers are the Clifford algebra 0, 1. And yeah, basically I is just a symbol. We don't really like think of it as a matrix. So how do people feel about this? Does this seem okay, or does it seem weird?
This is new to me, but I can see the logic here. Yeah, you kind of make it one more level abstract and.
Yeah, have people seen this sort of interpretation of complex numbers as matrices before?
Yeah.
Yeah, you've seen that. Yeah, so but like normally in high school or whenever you learn complex numbers, like you don't learn the matrix version usually. You just say I is just I, and then it's just a definition. So here is another example. So here's maybe a harder problem. You're told that sigma x, sigma y, sigma z all square to plus 1. And then also another thing is that they anti-commute. Kind of like before, option 1 is to convince yourself that, oh, well, these things are really matrices. And then if you fool around with matrices enough, you can come to the conclusion that these are what the matrices would be. So like, does sigma x squared, what does that give us? So that's like that, and then we multiply it by itself. And then like this times this gives us 1, this goes to 0, this goes to 0, and then this times this also gives us 1. So that's just like the identity, or like plus 1. And, if you go through all the other multiplications, you can figure out that like all of these square to plus 1, and then they all anti-commute with each other. So that's kind of the standard sigma matrices from quantum mechanics. Now, again, there's another option. The other option is just to treat the sigmas as like new numbers or new symbols with this, and I guess also the anti-commuting rule as a definition. So kind of like before with I, we saw you could think of I as like a 2x2 matrix, but you could also think of I as just a symbol with some definition for what it squares to. So we're doing the same things with the sigma, where we could think of them as matrices, but now we're going to think of them as just like symbols that square to something. So this, we've basically just invented the Clifford algebra 3-0. Sometimes people call that the algebra of physical space, or the APS. But basically, the number 3 is the number of symbols that square to plus 1. So we have sigma x, sigma y, sigma j. So that's 3 things that square to plus 1. And we don't have anything that squares to minus 1. So we have a 0 there. So that's why we call it the Clifford algebra 3-0. So how about this? Am I losing people, or is this sort of like a reasonable thing to do based on the last slide?
This is pretty good.
Okay. And I'm going to do one more. So now I'm doing with the gammas. So again, we have gamma 0 is squared as plus 1. The other 3 squared at minus 1. And then they anti-commute when the indices are different. So
sorry,
we've already seen...
Sorry for interruption. Yeah, I just wanted to add before we will go into 4-dimensional case that like geometrically you just can think about those equalities as basically first of all you kind of have just standard Euclidean 3D space with 3 basis vectors in there. So those 3 squared values which are equal to plus 1 are just directions in space, and that's kind of it. And anti-commutation relation is actually about the orientation of the plane element. So if you have 2 basis vectors multiplied, it means not only like a scalar product but also the wedge product. So you should think about that multiplication also a bit like a plane. So if you change the order, you have a sign change due to the orientation change of the plane. So geometrically it's kind of like it.
Yeah, I'm going to talk about the wedge product later, but that's true. When you have like sigma x, sigma y, that's sort of like a plane in the xy plane. Yeah, but anyway, so just like before, option 1, you can convince yourself that these are matrices, and just like Dirac, you can come up with these matrices that satisfy the squaring rules and the anti-commutation rules. But again, option number 2 is to just treat them as, their own symbols, their own numbers, and then they satisfy. This is just, again, that's just a summary of these 3 things here, where if we anti-commute a symbol with itself, we get 2 times either +1 or -1, and then if we anti-commute different symbols, then we get 0, because anti-commuting means they're equal to the negative of themselves when you switch the order. So this, here we've invented the Clifford Algebra 1-3, also called the SpaceTime algebra, and hopefully you can understand by now we have one symbol that squares to +1, so that's where the 1 comes from, and then we have 3 symbols, gamma 1, 2, 3, that square to -1, so that's where the 3 comes from, so that's why it's called the Clifford Algebra 1-3. Those were 3 examples of Clifford algebras. Oh yeah, and of course we need the anti-commuting rules as well. Hopefully that's enough examples where you could understand that the Clifford algebra PQ means we have P symbols, which are kind of like the gamma 0, that square to +1, and then we have Q symbols, these are some examples, that square to -1. So you could kind of invent any Clifford algebra you like just by picking a number of symbols that square to +1 and a number of symbols that square to -1. And then the other rule for Clifford algebras is that the basis vector, the symbols anti-commute with each other, or you could think of them as basis vectors. Yeah, so I think I have some examples. Oh yeah, another thing is sometimes if we're only using square positive symbols, we kind of just forget about that 0 and we just write CLP. So for example, the 3, 0, so that was like the one with the sigma x, sigma y, sigma z. You might see that written as just CL3 instead of CL3, 0, but they mean the same thing.
Yeah, actually you can switch them other way around also, and you'll get isomorphic Clifford algebra. So it doesn't matter if you write in P0 or 0P, because CLPQ is isomorphic to CLQP.
Okay, I didn't know that. Okay, so oh, sorry.
Is there always a matrix for any P and Q of Clifford algebras?
No.
Yeah, I think there is.
No.
No? Oh, okay.
No, because you can notice that we are kind of moving forward to the more richer division algebras. So you can build complex numbers from the real ones, you can build quaternions from complex, and while going higher and higher you will go, the procedure actually is called Cayley-Dickson procedure, I think, or algorithm, I don't know the right way to say it. So basically, pair of real numbers will give you complex numbers, pair of complex numbers will give you quaternion, pair of quaternions will give you octonions, and etc, etc. So you can continue that way. But while you are moving higher the tower, you will lose some properties, and for example, in the octonion algebra, you will not have associativity, and therefore there is no matrix representation, because matrix multiplication is associative operation.
So are the octonions a Clifford algebra though?
Yeah, I think they are. Yeah,
are they?
Yeah, because Cayley-Dickson procedure applies to them as well, and they will be just some kind of higher order Clifford algebra. That's it.
Okay, I'm actually gonna just take 30 seconds and see if I can look that up on my phone. Because I'm a little bit confused, so I'm gonna say are octonions Clifford algebra.
Yeah, I'm not 100% sure, so maybe let's check that.
Would that be CL07?
Yeah, probably, yeah.
So the first result I see, so this is the internet, so it could be wrong. The first result I see says the octonions are not a Clifford algebra since they are non-associative.
So in Clifford algebra we have associative. Okay. So
maybe we do. I think like the super technical definition of a Clifford algebra is, and I didn't include this because I thought it was like symbol hell. It's basically like the tensor algebra over. So like if you have a vector space, like say it's 3-dimensional, the tensor algebra would be like linear combinations of 1, v1, v2, v3, and then you have v1 tensor v2, v2 tensor v3. You can get like all the combinations of tensor products. And then you do what's called what's the word? Quotient.
Quotient, yeah.
You basically say that a vector tensored with itself is equal to that vector under the metric. So it's like squared length. So what you're basically saying is that when I have v tensor v, instead of leaving it alone in my linear combination, I can sort of cancel it out and get like a +1. And I think the tensor product is associative, which might be why the octonions are not a tensor algebra.
Yeah, then probably it seems that Cayley-Dickson construction reach out like the kingdoms of the Clifford algebras and just goes beyond.
Yeah, so that what I just wrote, if that confuses you, I wouldn't worry about it too much. I feel like that's something you should learn maybe like after you've already had a lecture on Clifford algebras. It doesn't work with my intuition very well, but it's like the technically correct definition you might see in some papers.
Yes,
so I was going to move on. Are there any other questions before I do?
Yeah, I just wanted to say that it would be interesting to take a look at the octonion representations later someday.
Yeah, like that's a whole other topic. Maybe we can talk about that later, but I'm probably just gonna not talk about that now.
Yeah, the octonions are utilized in a few constructions in quantum field theory. John Bayes did a lot of work with them in the octonion construction of the standard model. If you are interested in citing that later, just throwing it out here.
Okay.
Yeah, I think that Mesocosmos actually shared a few seconds ago John Bayes' notes on the octonions.
Oh, okay. He did? Oh, I didn't see that.
Yes, exactly.
Yeah, now I'm seeing it. Yeah.
Okay, so I'm gonna keep going if that's okay.
Yeah,
so,
let's continue.
People were talking about matrix representations. I think the answer is that you can give a matrix representation of any Clifford algebra. It's definitely at least true for the simpler ones. So, like, we've seen with the complex numbers, which are, 0 symbol squared to +1, 1 symbol I squares to -1. I showed you the matrix representation of I already. And 1, I'm not saying it, but 1 basically always is the identity matrix. Something else you might not have heard of is called the split complex numbers, where it's sort of like the opposite. You have a symbol. I called it P for positive, but I don't know what you normally call it. But basically it squares to +1. And you would have almost the same matrix, except you have plus here. And you can check that squaring that matrix gives you the identity instead of minus the identity. The Clifford algebra 0, 2, where we have 2 symbols, I and j, that square to -1. Also, you can call, this is not a new symbol, ij. It's just kind of like, you could call it k. It's sort of just like another name, but it's not technically a third symbol. It's just I times j. those are the quaternions, because I squared equals j squared equals ij squared is -1. So the quaternions are a Clifford algebra, and those I think give you like a matrix representation of that. And then there's the 3, 0, which again, that's called the algebra of physical space. That's with the sigmas. They square to +1 and they anti-commute. You've seen those. And then again, the space-time algebra with the gammas. I didn't write out the matrices, but yeah. So I think it is a rule that you can always come up with a matrix representation if you want to, but you kind of just think of them as their own symbols if you're just talking about the Clifford algebra. You don't necessarily have to think of them as matrices. And where was I going to go next? Yeah, so basically if you have a vector space, like a familiar vector space, you can always get a Clifford algebra from it. And basically the rule is when you have a metric, that will tell you how to square the basis vectors. So if, like our standard Minkowski metric, this, the metric G tells us what the squares of the basis vectors are on the diagonal. But you can imagine any metric you want. Like you could have a -1, +1, -1, and that would give you CL, I guess 1 and then 2, because you have 1 plus and then 2 minuses. So the metric will tell you how to square the basis vectors. And then you just, basically, if you have this and you have the anti-commuting rule, where like, the multiplication works backwards with a minus sign, you can actually start adding linear combinations together. And I guess the interesting thing with Clifford algebras is that you can add scalars, vectors, bivectors, and trivectors all together in the same expression. So that might be a bit weird. Like, you would normally think, oh, you add vectors with vectors, but you can't add a scalar with a vector. But in Clifford algebras, you can. Like, if I have, 2 plus 5i in the complex numbers, the scalar and the vector I kind of, you can add them together. Or in the quaternions, if I have 1 plus I plus j plus k, the scalar and the vector parts all kind of live together and you can add them together.
Yeah, so I think it should remind you about the exterior algebra actually, where you can kind of add
so
some planes
this is
and
almost
cubes.
exactly. Oh, sorry, someone was saying something.
No, I was just continuing the...
Okay, yeah, so this is basically, and I talk about this later, maybe I didn't explain everything in the correct order, but the exterior algebra is basically this. You would normally write it with the wedge product in the middle. It's just a slightly different notation. Where when you have the wedge product and you reverse the order, you get a minus sign. The Clifford algebra is like the exterior algebra that also has a dot product. So I'll talk about this on a later slide, but it's like a dot product and a wedge product living together. So it's kind of like an upgraded version of your exterior algebra. Yeah, so I just wanted to make it clear, vectors, bivectors, scalars live together, so you can add them. So, 4 plus 3i, 4 plus 3p in the split complex numbers. These are the quaternions. Again, you could think of that as I, j, and k, and that's 1, or 1, 2 times 1, 3 times I, 4 times j, 5 times k. I think it starts getting pretty interesting in CLO3. So the reason it's called the algebra of physical space is that these are the basis vector directions, x, y, and z. And then these are the bivectors. So x, y would be a plane like that. Y, z, I guess, would be a plane like this. And then x, z would be a plane like this. And then that's the trivector, which is kind of like a cube. So you can, instead of just dealing with vectors, you deal with kind of all the possible combinations of shapes that you can get with vectors of all the different dimensions. I guess the scalar would be like a point. Yeah, and then again, the Clifford algebra, you get tons. You get 16 different combinations of things you can make. Now I wanted to say that Clifford algebras are kind of diamond shaped, so hopefully I'll show you what that means. And then in the you can start seeing where the diamond is coming in here, especially with the algebra of physical space. You have your scalar here, and then these are your three vectors, which are again that's sort of like, you know, your directions like this, and then your bivectors are sort of like your planes. Your three possible planes in three-dimensional space, and then your trivector. Also, it's sometimes called the pseudo-scalar. I think bivectors are sometimes called pseudo-vectors as well. I think like angular momentum, you're normally thinking of it as like a vector in sort of intro to physics classes, but it's much better to think of it as a plane. So a pseudo-vector or a bivector. That makes a lot more sense, because like you have, instead of an axis, you have a plane of rotation. And then the big one is the space-time algebra. You have your scalar, 4-dimensional vectors for your space-time, 6 possible bivectors, 4 possible trivectors, and then your pseudo-scalar at the top. So hopefully you can kind of see how Clifford algebras, they're always diamond-shaped, scalar at the bottom, and then you can kind of build them up, and then they bulge at the middle, and then as you build more and more, there's fewer combinations, so they're kind of always shaped like a diamond in terms of the basis vectors. Also, when you're counting, here we have 2 dimensions, 2 dimensions, 4 dimensions, 8 dimensions, 16 dimensions, so the dimension's always a power of 2. So when you take a vector space of dimension n and turn it into a Clifford algebra, you always get like 2n basis elements. So like in 3D, where we have like x, y, and z, the Clifford algebra is 8-dimensional because there's 8 possible combinations of vectors. And then in space-time, space-time's like 4-dimensional, but in the Clifford algebra you get 16. So 4 and then 2 to the 4 equals 16.
I just wanted to...
Yeah, and here I was going to... Sorry?
I just wanted to say that those diamond-like shapes are just like connected with combinatorial nature of those things. So we just basically taken the combinations, and it's the same as Newton's binomial theorem.
Yeah, so this is like 4 basis vectors, choose 0, so you get 1. This is 4, choose 1, which I think is 4. This is 4, choose 2, which is 6. 4, choose 3, which is 4. And then this is 4, choose 4, which is
so you just summon them all and getting 2 to the power of n at the end.
Yeah, I think it's a rule where if you sum over k, you always get like 2 to the n. But I don't remember the proof for that off the top of my head.
Yeah, that's true.
So I'm going to talk about the dot product and wedge product now. So basically, so the rule in a Clifford algebra is things will square. Here we're squaring to +1, but it could be -1, and then reversing the order gives you a minus sign. So if I have u and v, and I write them as linear combinations, what am I going to get? So we can do FOIL, like first, outer, inner, last, and we get 4 terms. Now this is going to go to 1. This is going to go to 1. And then I think this here, we can write it as -e1, e2. So that's 1, and then we get a minus sign because we swap the order here. And then if we summarize all that, we get this as a scalar, and then we get this as a bivector. So this is kind of interesting where if you have like a vector multiplied by a vector, you kind of get a scalar plus a bivector. So it kind of, if you have a 1-dimensional thing times a 1-dimensional thing, you get a 0-dimensional thing and a 2-dimensional thing. So that's kind of an interesting idea of how Clifford algebras work. And then, so this is basically the dot product, which is a scalar, and then this is a wedge product, which is a bivector. And you can see here, if I did this in the opposite order, then this would be a plus and this would be a minus, which would be negative, I guess, negative u, v, which is also positive v, wedge u. So basically the Clifford product, you could do it the other way, like manually with the components, but you could also say it's the dot product plus the wedge product if you wanted. Now I think if two vectors are orthogonal, which means their dot product goes to 0, then the Clifford product is just the wedge product. So that's why basis vectors, we can swap their order if they're orthogonal, because the dot product part goes to 0 because they're orthogonal. So we can just treat it as just the wedge product part, which is why we can reverse the order. And then there's if vectors are parallel, so if we have like this, and we take their Clifford product, then the wedge product goes to 0, and then we can swap their order with just a plus sign.
Yeah, and if we have a matrix defined, we will use it instead of this scalar product, or like define scalar product in terms of the matrix, right?
Say that again, sorry?
Yeah.
Oh, like to figure out what the scalar is?
No. I just mean if we have a matrix defined in the Clifford algebra, some G, then it will impact the scalar product. So we will have scalar product defined in terms of the matrix. And I've been thinking about wedge product. Will it impact somehow the wedge product or no?
I guess I'm not sure. I don't really know how to answer that. Anyway, I might keep going if that's okay.
Yeah. Let's continue.
Yeah. So basically, the dot product gives like the squared lengths of vectors. So these are scalars. And then the wedge product basically gives a bivector. So u wedge v is basically you take u and then you put v and you make a bivector out of that. So you can see this is sort of going in this direction. I guess that's counterclockwise. But v wedge u, you do this and then this, so you kind of go in the clockwise direction instead. So that's why the wedge product anti-commutes, is because if you do it one way, you get a clockwise orientation, and if you do it the other way, you get a counterclockwise orientation. So that's something to keep in mind with the wedge product. The planes always have an orientation, so so basically there's the array interpretation of the Dirac equation, where like our spinor here is going to be a complex column. And then, but what I'm trying to show is that you don't need to interpret these as matrices. You can sort of start thinking of this as just vectors in a Clifford algebra. And then the spinor is also going to be a member of the Clifford algebra, which is going to be the topic of the next section.
I'd like to mention, sorry to interrupt. I'd just like to mention in the previous derivation that you gave of the of the relationships of the Clifford product, the scalar plus the bivectors were spinors. I found that to be relevant to mention. The
scalars plus the bivector. Okay, that's interesting.
Yeah.
So you're saying it's like the even members of the Clifford algebra are spinors?
Well,
is that what you're sort of hinting at?
The product of two vectors in a Clifford algebra is a spinor. You see, that's what I'm saying. If you look at the physical interpretation of these elements, so for example, I don't know, a basic bivector like angular momentum, for example, it's no surprise, and you may be covering this later, I don't know, but it's just that in the definition previously of how to multiply these vectors out, whenever you multiply these two vectors in the Clifford product as you define here, that's a spinor right there. And it turns out that if you were to attach physical meaning to this spinor, utilizing physical entities of bivectors, of angular momentum, and so on, you actually end up with the Dirac equation by taking a look at a few trivectors, like a bivector like the magnetic field, or so on and so forth. I found that to be an interesting fact. Useful.
Okay, so this next section will be interesting because Because I think Slava and I have been sort of, I don't know if we've been arguing about this, but I've been confused about this. There's like two separate definitions of spinors that I've come across. It's sort of what you're describing. And I think like Hestenes came up with it.
Yeah, so there's a lot of confusion over spinors because they are so ambiguous at times. The way I'm not a mathematician, I'm a physicist, so I can only claim to know what I know about physics. But in terms of the Clifford algebra, the way that I was taught to think about it, reading books and everything else, was that a spinor got its name originally from the Clifford algebra because if you multiply a spinor by a vector, it actually rotates the vector by the amount proportional to the length of the magnitude of the spinor. You see? So if you were to actually multiply everything out and construct the picture, which I painfully done when I was learning it, the spinor got that. And it actually is called sometimes even the rotor in older texts because of this. And then it got generalized by, fellas at differential geometry and so on. But I found that to be interesting because it's actually very physically intuitive when discussing spinors and Dirac equation and quantum mechanics and so on. To me personally.
Right. So I think where I'm going to go in the next couple slides is sort of what you're talking about. But the second half of this talk, which is immediately after, is going to go through another definition of spinors, which says that spinors are minimal ideals, which I don't know if you've heard of that one before, but it's kind of different.
I've heard of that, but I don't understand it, and that's just my physics career. So
maybe this will be instructive for you then. So I'm going to move ahead. So we understand
sorry, guys.
what spinors... Oh, sorry?
I just wanted to add one more note here, that it seems to me that I have understood a bit more a few seconds ago while looking at those plane elements on the previous slide, and while ARBB was talking about the history of the name spinor coming from their action on vectors as rotors. And I just wanted to say that every plane in any space will always have a normal vector assigned to it. And basically that normal vector will be kind of like a rotational axis for any geometrical unit in a space. And magnitude, kind of the area of the plane and its orientation, can tell you how much to rotate that vector. So actually you can convert that plane into a flag. So you have the flagpole analogy here directly from the plane.
Yeah, well, like one thing that, like, if I might say one thing, if u and v are unit vectors, or I think even if just like, let's say that they're unit vectors. If I take uv and I multiply it by u, then the u's will just cancel out to 1 and I get v. So you can almost think of it as uv rotates v and u into v. So it does the uv angle rotation basically. You can think of it that way.
Yeah.
And, you know, like...
Yes.
Yeah. So I think what you're talking about is sort of called spin groups, I think. So I'm going to talk about spin groups now. We're almost at the end of this section, and then we can take a break. I know your brains probably hurt a little if this is new. But there's a group called spin PQ that lives inside Clifford algebra PQ. So if you recall I guess some of you weren't in the previous call last week, but you'll recall that we found like the 2x2 complex half-angle matrices. So like this was an example here, and that would do a rotation on your spinor in the YZ plane. And it was actually just a combination of like the identity. You can see how cosine is on the identity diagonal, and then like a pair of sigma. Sigma is multiplied by sine, which in this case give you the off diagonal. But basically, we can think of these as being not as matrices anymore, but as being like Clifford algebra numbers. So like we have a scalar part and a bivector part. So these are things that live inside. In this case, it would live inside CL30.
Yeah,
and
so
there's special...
you can just think about those as basically vectors lying in the corresponding bivector plane. Like sigma x, sigma y will be xy plane. And you can think about those as vectors in those planes.
So basically the even graded, when I say even graded, I mean like sigma x, sigma y, sigma z are odd. The pairs would be even. And then I guess the trivector would be odd because it has 3. And then I guess the scalar, I guess just 1 is even as well. So these are all even members because they have the scalar and the bivectors. So the even graded members with norm 1, so they square to 1. I don't know, b squares to 1. Those are called the spin group for that Clifford algebra. And basically they correspond to rotations. So like again, if you were here, like these are members of SU2 basically. Here. And so spin 30 is actually the same thing as SU2. The matrix interpretation is just SU2. So I might skip some slides here because I've been going on for over an hour, and I might come back to this stuff later, but I think for now I'm just going to end the section and we can do a Q&A and take a small break. So I guess the main thing is that like a Clifford algebra PQ, you have P symbols that square to, you square them to +1, you have Q symbols, and that you square them to -1, and then they anti-commute. And so like the complex numbers, the quaternions, the sigma matrices, and the Dirac matrices, these are all examples of Clifford algebras because they follow these rules. And I guess it's also good to know in the case of like rotations in 3D space, that's like spin 30, and those are like linear combinations of 1 and like the even bivectors. There's also spin 1, 3, which give you rotations in space-time. 3 of them are like actual physical rotations, and then the other 3 are boosts, like Lorentz boosts.
Yeah, and
boost is like a rotation in like time and space.
You're actually getting quaternions, unit quaternions for spin 30, right?
Yeah, sorry, they have to be a unit norm. I forgot about that because like not every single quaternion does spinning. It has to be like unit length quaternions. Kind of like how like a complex number can be written as like a magnitude and a phase, but you need magnitude 1 in order to just do a spinning. Otherwise, you get spinning and scaling. So you have to they have to have unit norm. Otherwise, they might like do some scaling and spinning, as you can get both.
Mm-hmm.
So I realized that was like over an hour. Do people feel about this so far?
I'm ready.
Are your brains hurting?
Pretty good.
You're feeling okay?
Yeah.
Okay, so the next section is probably going to be new to basically everybody, and this is spinors are minimal ideals.
Sorry, Chris, I just wanted to leave one more note about the last slide.
Yeah.
Even the previous one, but it doesn't matter because you skipped a lot of things.
I skipped a whole bunch.
Yeah. I just wanted to tell that you have seen that we have normed even graded members as spin group, and spinors could be defined as an objects which are transformed through the spin group. So basically you will have a transformation rule for spinors, like psi apostrophe equals element of spin group multiplied by psi. So, and you can notice that like when you multiply even graded members by even graded members, the parity will be conserved. So spinors could be identified, and actually it's proved that they are just even graded members of the Clifford algebra. Not enormous ones.
So I've mentioned this before. The definition of spinor that you just gave is going to be a bit different than the definition of spinor I'm about to give.
Yeah, probably. I'm interested into understanding how to connect those and in what matter they are different exactly.
Yeah. So I guess I'll just start, and maybe we can connect the dots after. So
yeah.
I guess this should be spinors are members of minimal ideals. And again, if you've never taken an abstract algebra class, you probably don't know what an ideal is, so I'm going to go through that. So the two things to understand for this section are projectors and ideals. And I promise at the end we're going to get to spinors and Clifford algebras, and hopefully everything you've seen will come together. But first we're going to start with these two math concepts. So a projector is also called an idempotent. Projector is definitely easier to say. Basically, it's an operator that has the property that where if you square it, it just goes to itself. So if you have like a vector and you like project it down to like the ground, you get like, something like this. And then if I project that vector down to the ground again, well, nothing's changed, right? So basically, applying a projector once is the same thing as applying it twice. Or that's the same thing as applying it 3, 4, 5, 10 million, 850 million times, because it squares to itself. So if you've projected something once, you can project it 1,000,000 times and get the same result. I'll show you some actual matrices that are projectors later, but this is like a algebraic definition. Another definition, two projectors are orthogonal if they multiply to give 0. So for example, here I showed a projector down to the ground. If I wanted to project against this wall, that could be another projector. But if I project against the wall and then project it against the ground, then I have nothing left. I have like a 0 vector. So when two projectors, like if you apply them one after another and you have 0, because they're like orthogonal directions, you just say the projectors are orthogonal. So they multiply to give 0. Also, if I have a projector, there's kind of, I don't know what the word is, I called it a partner, but it has an orthogonal projector partner called 1 minus p. So just a quick algebraic proof of that. If to show that this is a projector, we just square it, 1 minus p times 1 minus p, and then we just, FOIL that out, 1 minus p plus p squared. But of course, p squared, p is a projector, so p squared is just p, and then that cancels with that, and we have 1 minus p. So if p is a projector, 1 minus p is also a projector because it squares to itself. And it's also an orthogonal projector because if we multiply them, we have p minus p squared, which is p minus p, which is 0. So this is an important fact we're going to see over and over again. If p is a projector, 1 minus p is an orthogonal projector. It's kind of like its opposite almost, or its partner. I don't know what the word is. So that was all abstract algebra. Let's see some actual examples. So this matrix here will project out the x component of a vector. So if we have like x, y, z, then this just gives the x. And then this would do the same thing for the y component. So this would just project out the y component. So those are some projectors. Oops, I should not have written that. So these are also orthogonal. So multiplying these two gives the 0 matrix. And the reason is kind of like I showed before, if we project on the x-axis like that, and then we project on the y-axis, we get nothing left, so it's 0, so that's why they're orthogonal. Also, fun fact, the sum of two orthogonal projectors is also a projector, so if we add these together and square, the neat thing is these parts will go to themselves because they're each projectors, and because they're orthogonal, the middle parts go to 0. So we just get what we started with. So that gives this matrix, which is like projecting in the xy plane, basically. So when we add the x projector and the y projector, we can like project something into the xy plane, basically. So these are just some fun algebraic facts we're going to use later. Okay. This is one other term. I know there's a lot of definitions, but a projector is called minimal or primitive if we can't write it as a sum of projectors. So like this would be not minimal because we can write it as a sum of two projectors, whereas these up here would be minimal because you can't write it as a sum of two projectors. It just doesn't work. Okay, that's a lot of definitions. Is this fine? I don't think it's too hard, but anyone have any concerns here?
No, fine. Absolutely.
Okay.
Fine.
Okay, so now let's talk about some projectors in our CL030 algebra. So I'm not going to use the matrix interpretation, but here's a way we can get projectors in this algebra. So if we take a unit vector u, we can get a projector. So z is like a unit vector, sigma z. You can think of that as like just the sigma, the z basis vector, and it also squares to +1. So we're going to use this to make a projector. That this definition here is a projector. So 1 plus sigma z times a half, that gives p plus. That we're going to call that projector p plus. So I don't remember if I wrote a proof of this, but I will do it super quick here. So that gives us a 1/4 times 1 plus sigma z plus sigma z plus sigma z squared, which goes to 1. So we have two 1s and we have two sigma z's. So that means we can just write that as a quarter 2 plus 2 sigma z, and then these 2's we can turn that into a 1/2. So this is, before I showed you some matrix projectors, this is a projector where we're not seeing matrices at all, we're just seeing like pure algebraic symbols, but it still works out that this squared gives itself. Are people okay with that? Yeah, okay. So, and then remember how I told you 1 minus p square, p plus will also give you a projector, and we're going to call that p minus. And this is like an orthogonal projector pair. So p plus p minus equals 0. That's kind of like when you project. These are not x and y axes, but just as a general kind of metaphor, that's like projecting along two different directions, and you end up with nothing at the end. So those are two projectors in our Clifford algebra. And you could do this with any unit vector u. So you could pick any direction you wanted, but we're just using sigma z for simplicity. Okay, so now you could give a matrix representation, right? If you wanted. So 1 is just the identity matrix, and sigma z that's the sigma z. So it just gives this simple little matrix here. If you square that, you get the same thing back. And for p minus, we just change this plus into a minus, and we get this matrix here. So if you like matrices, it'll be more obvious that these both square to themselves, and it's also more obvious that they multiply to give the 0 matrix. But the matrix representation is kind of optional. You don't necessarily need it. You could work with just the symbols in the Clifford algebra. Okay, so yeah, we have this projector. Yeah, I think, yeah, so this p minus is 1 minus p plus, and yeah, so that's where the minus sign comes from. You could either just think of it as flipping the sign, or you could think of it as 1 minus p plus. They end up being the same thing. So basically if we were working in the xy plane, you could think of projecting a vector into two parts. You could think of it as projecting out the x part and also projecting out the y part. So you could think of every vector has an x projected part and a y projected part. And in our case, these two projectors are going to give us a p plus part and a p minus part. So every single, in our 8-dimensional, it's harder to visualize because this is 8-dimensional, but basically any element in our 8-dimensional space has a plus part, which is just the p plus projected out, which is this. And then there's also the p minus, which is just the p minus projected out part. So just as an xy vector has an x part and a y part, all of our Clifford algebra elements have a plus part and a minus part. It's obviously a lot harder to imagine in your head with this, but it's kind of the same idea as over here. So yeah, so basically we could add an x and a y vector back together to get the original, and we can add our plus part and our y part together to get the original. The reason is that p plus and p minus are just 1 when you sum them together. So hopefully, like p minus is literally defined as 1 minus p plus. So if we add p plus to that, it's obviously 1. So this fact is like, by definition, it's kind of trivial. But the important part is we can project out an element of the Clifford algebra and then put the parts back together to get the original. So yeah, so this is more of a summary. So this is like a matrix projector that projects out the z component. And then this would be another one that projects out the xy components. And they're actually like an orthogonal pair. Like if we take one and subtract the z projector, then we get the xy projector down here. And then, yeah, we have the plus and minus projectors, and yeah, they're basically orthogonal partners. 1 minus p plus gives you p minus. Okay, so do we have any questions before I move on? Just projector stuff?
In regards to the projectors, you're giving an example in this particular three-dimensional space, but like in different metrics, is it different? So maybe in SpaceTime, the Clifford SpaceTime algebra, is it any different with the projectors? Is the time projector?
So I think like as long as this is a unit vector in any Clifford algebra, you're going to get a projector. So like you could come up with, there's like an infinite number of projectors, and it works the same in space-time. I just picked sigma z. You'll see why I picked it later, but like, yeah, you could invent, there's like an infinite number of projectors you could come up with, basically.
Okay.
I think I do show space-time later. That's where, yeah, I'm starting with 3 dimensions because it's easier. Space-time is a bit harder, but I do show that later, so.
All right. Thanks.
Yeah, so I'm just gonna, so these are some math definitions, just because I'm assuming some of you have not taken like abstract algebra. So a ring is just a word for a set where we can add, subtract, and multiply. So like the integers and like matrices are rings because you don't like matrices, you can't always invert them, so you don't always have like division, but you always have plus, minus, and multiplication. So yeah, so like integers and by matrices, those are a ring. An algebra is basically a vector space with a product. So like a Clifford algebra, the reason we call it an algebra is because we have a way of taking a product, which is this Clifford product. So that's why we call it a Clifford algebra. We can do a product between vectors. So normally you can always add and subtract vectors, but we can also product vectors in an algebra. So yeah, so like the Clifford algebra has a Clifford product. Okay, so here's the definition of an ideal. It's a bit abstract, but I will get to, I'll show some examples to make it less abstract. So an ideal is a subset of a ring or an algebra. So it's a subset of like a set with like plus, minus, and multiply defined on it. I've heard it described as a bit like a black hole. The reason is if we have two members in this ideal subset, their sum is going to stay in the ideal. So like if you just add two ideal members together, you're not going to escape the ideal, you stay inside. And then the other definition is the product of an ideal member and any other member that is not in the ideal will send you into the ideal. So I have examples coming later, but just like if this is our algebra and this is our ideal, if we take this and multiply it with this, what's going to happen? We just get sucked back into the ideal. So I know that sounds like really abstract, like what does this even mean? So I'll give some examples. So yeah, so that's the definition. Two ideal members need to sum to an ideal member, and the product of an ideal member and any other member goes to the ideal. So very basic example is the multiples of 3. So like, like 0, 3, 6, 9, 12, and I guess also -3, -6. That's an ideal. So why? Well, the sum of two ideal members gives another ideal member. The sum of two multiples of 3 gives another multiple of 3. Hopefully that's not hard to see, like 6 plus 18, 24, another multiple of 3. So like, yeah, and like obviously 3n plus 3m gives a multiple of 3, not hard to see. Also, a multiple of 3 times any integer gives another multiple of 3. So, 3 times 7 is a multiple of 3, which is not surprising. So, like you could see when I was talking about the integers, and then like the multiples of 3, if we have a multiple of 3 and any other integer, we multiply them, we get sucked back into the ideal, we get a multiple of 3. So this might seem like kind of a dumb definition for something that's like simple in this example, but are people fine with this so far? I'm going to give another example with matrices next.
But
yeah,
why
okay.
is there? But why is there a particular reason why these ideals happen, or are they just kind of like coincidences?
I don't know exactly why. Well, I'm going to show you the best reason I have related to this presentation is that projectors give you ideals. Like when you project stuff down, the place where it ends up is an ideal.
Yeah, and
that's like skipping a few slides ahead. I don't know if I have like a better answer than that right now.
Yeah, I just wanted to say that basically it's just all about the invariant subsets or subspaces of your bigger space. So it's the same way you're kind of chunking the molecule into simpler things like atoms. And you can observe that in a group theory where you have simple groups, right? Where you cannot split them into more simpler ones. And it's kind of the same thing, just called the other way around. So ideal is just like an invariant subspace, like atom.
Yeah, so this is a metaphor. It's not something you should take super literally, but like if I'm on the x-axis and I add some vectors in my x-axis, I'm going to stay on the x-axis. Like I can't escape if I'm just adding x things together. And same on the y-axis, I can't really escape if I'm just adding the y. But if I add a y and an x, I can get new stuff.
Right.
And that's sort of how ideals work, where like you can have an algebra that has all these ideals, and on their own, they can't really leave their own ideals. They're like, but if you go between many ideals, you can add them together and get new stuff you've never seen before. So this is like a metaphorical picture. I wouldn't take it too seriously because anyway, okay, yeah. So here's a slightly more complicated ideal. If we have 2 by 2 matrices and the first column is non-zero, I should have said the second column is 0. Brain mistake there. But basically, yeah, so a matrix that looks like this, summed with a matrix that looks like this, gives us another matrix that looks like this, where the second column is all 0. But the addition property works. Now, what slightly less obvious, you might have to think about it for 30 seconds, is if you have this and you multiply on the left with a matrix, then you end up getting a 0 second column matrix. So this is pretty obvious. This one is maybe a bit less obvious, but like you can check, like basically if you multiply this column by this row, you get 0, right? Or if you multiply this by this, then you get 0. So I think it's obvious if you think about it for like 30 seconds, but it might not be super obvious like at first glance. And another important thing is that this only works from the left. If I were to ABCD on this side, it would not work out. So ideals can be left-sided and right-sided. So this is what we call a left ideal, because all the multiplication has to come from the left side. So this is what we call a left ideal, matrices that look like this in the larger set of 2 by 2 matrices. So this set of matrices that look like this is a left ideal. If we multiply it from the left, it gets kind of sucked back. So again, if we have like, this is like our 2 by 2 matrices, and in here we have like our matrices that look like this. If we have this and this and we multiply them, we get sucked back into the ideal from the left only. Now, an example of a right ideal, instead of going by column, we have it by rows. So like the second row is all 0s. And this one you multiply on the right. So this is a right ideal because we're multiplying on the right, and we get stuck in the set of like the first row non-zero, second row 0. So these are like slightly less obvious examples of ideals, and they have like a left and a right side to them. So I think I talked about this before. This is like a metaphor. Like, you can think of like x is like the projected part of the x vector. Y is like the projected part of the y vector. Z is the projected part of the z vector. When you add all these different parts up, you can get something new. And this is kind of like we can add different ideals together, different ideal members together, and get something we've never seen before. So like the set of 2 by 2 matrices is sort of like cut between these like two different spaces, like this, like that ideal, and then like this ideal. And if we add them together, we can get something new that doesn't live in either ideal. So is that okay so far? Okay, I'm going to assume it's okay because no one's talking. So,
Yeah.
Okay, so here's what I was saying before. There's a one-to-one correspondence between projectors and ideals. So this is our P plus projector. That's our P minus projector. If we P plus and left multiply, then we get a member of an ideal. So like this projector, P plus, is in like an exact correspondence with this ideal. It basically creates this ideal when we multiply on the left. Similarly, our P minus, when we left multiply, we get the other column. So if you remember how I was talking like, oh, well, we can take M and we can break it up into a plus part and a minus part, but then we can add them both together and get M back. This is a more concrete example of that, how we can split a matrix into like a first column and a second column, and then we can add them back together to get the original. So the lesson here is that ideals and projectors are kind of like always together. If we have a projector, it's going to create an ideal for us.
The P plus is both a left and a right ideal, though, right?
Yeah, so if I were to do on the right instead, I would get this. And if I do p minus and multiply on the right, I get this. So they can create left ideals or right ideals. It depends on what side you're multiplying. When you multiply from the left, you get left ideals. If you multiply from the right, you get right ideals. Yeah, I summarized this here. This is a left ideal. That's the p plus left ideal. This is the p minus left ideal. This is the p plus right ideal, and then this is the p plus right, p minus right ideal. So that's multiply from left, multiply from left, multiply from right, multiply from right. Okay. Yeah, I think I tried to like give like a formal proof on this slide. So like if we have two projectors, you could think of it as p plus and p minus, where they add to 1. The p1 gives us an ideal called I1. So like it doesn't really matter like how many matrices you multiply on the left. You're always going to get like a first column matrix. So I'm trying to say that here. It doesn't matter how many things you multiply on the left, you're never going to escape this ideal. And yeah, so I2, and then the same thing is that the second projector will just give you that, and it doesn't matter how many things you multiply on the left, you're never going to escape. And also the only element that they have in common is the zero matrix. I'm trying to think of like an intuitive reasoning. I think it's like if like I said before, like if two projectors are orthogonal, if you project using one and then project using the other, then you get like 0. There's nothing left. So if you assume that, oh, well, I have some R that lives in the first ideal and it also lives in the second ideal, well, the only way that can happen is if we've used both projectors, which means it has to be 0. So like 0 is the only thing that the two ideals have in common. Yeah. So basically, because the only thing they have in common is 0, that means that an algebra, when we break it up into ideals with like p and 1 minus p, I call that p1 and p2, you can basically kind of split an algebra up into two ideals, and then you can this is what I've just been saying all along. Like if you have the plus part and the minus part, you can always bring them back together to get the original. So that lives in one ideal, that lives in the other, and the entire algebra is just the direct sum of the two ideals. Okay, so this slide was a bit more abstract, but is this like at least kind of intuitive? If you have a projector and you project down your space, you're going to get an ideal. If you have an orthogonal projector, that's going to give you another ideal. And those two ideals are sort of like the building blocks for everything in the algebra. You can take something from the algebra, split it up, and then put it back together. That's what I'm trying to say. Yeah, okay. So, clearly I was trying to say something here. Yeah, so basically in our spacetime algebra CL30, these are kind of our important two orthogonal projectors, p plus and p minus. And they split CL30 into two ideals, I plus and I minus. And I'm saying spinors are elements of ideals. So the things that live in I plus and I minus are spinors. So let's see what that means. So vectors, do you remember how I said that like if we have like an ideal here and an ideal here, alone we can't really escape them, but if we add them together we can get something new. So vectors, spinors live inside these two, but vectors, we can't get vectors from either one alone. We need them both. So like spinors live here, spinors live here, but vectors only live when we in the bigger space where we add them together, which is like I plus direct sum with I minus. Yeah, if we add spinors from each ideal, we can get vectors. So yeah, so like basically if we have this vector and we get the plus part of it and get the minus part of it, then we can add the plus and minus parts together, and these become 1, and yeah, so basically we can split up any vector into 2 spinors by projecting out the 2 parts of it. So this probably doesn't make sense yet. I think I show you what spinors actually look like. Okay, so what I did, CL30 has 8 basis vectors, right? I basically act on them with P plus and P minus to show you what the spinors look like. So I have the 8 basis elements here, scalar, 3 vectors, 3 bivectors, and 1 trivector. And then I act on, so that's x is just whatever these things are. Then I act from this side using P plus. So this is going to give a left ideal because we're multiplying x on the left. So 1 times P plus just gives P plus. That's not hard. If we multiply this on the left, one thing I should have said, I is called the trivector. I think it squares to -1. That's why they called it I, because it's sort of like a complex I, but not really. And I think its matrix representation, I should have had a slide on this, but its matrix representation is like I times the identity. So it's useful. It's a useful way to write this in shorthand. So here I'm showing that xz is -y times the trivector. So basically the reason is if we take xz, we can put yy in the middle, because yy is just 1, right? That squares to 1. And then we can swap 2 of them, so let's swap these 2. So we get x, y, z, x, or y, and that has a negative sign in front. And then this becomes I. Sorry, I should have had a slide on that, but basically this I, it's just the trivector x, y, z, and it's used to like save space, basically. So I'm sorry about that if that's confusing. Yeah, so if we multiply this onto the projector, we get this. If we multiply y onto the projector, we get this. We multiply z onto the projector, we get this. Now you'll notice that we got the same thing twice here, which is interesting. If we multiply xy onto the projector, we get this. If we multiply yz onto the projector, we get this, which this is actually the same as this, so that's interesting. This multiplied onto the projector gives this, which is almost this is almost this. I think they differ by a factor of I. So like you can get that by multiplying by big I, the trivector. And then here we get the same element as right here. So the 8-dimensional space kind of gets projected down to a 4-dimensional space because we get repeated results. Are people okay with this? Yes, I know I keep asking this, but I want to make sure I'm not losing you. Okay, so we have an 8-dimensional space.
No, continue.
Yeah. No. Well, you can go ahead and ask if you have a question.
No, it's just that it reminded me of I'm not because I'm being stupid right now, but you know, these really are just Pauli matrices right now, and right? Just to
yeah. So as I've said before, you can think of them as matrices, and I'm going to show you what the matrices look like, but you don't have to think of them that way. You could think of them as just abstract symbols in your
As just individual
algebra.
elements of the algebra.
Yeah, and I think I'm going to show you what these matrices look like. If I asked you what these matrices look like, you would probably have no idea, but they don't look very hard. They're very easy, actually. But yeah, we'll get to that later. So yeah, we have an 8-dimensional space, and this projects it down to a 4-dimensional space. And if we use P minus instead, we get another 4-dimensional space. And it turns out we basically just have to reverse a bunch of signs. And we basically get... So, like, we're reversing the signs of some things, but not others. Like, this is still a +1, this is still a +x, +y. So, they look the same, but it's actually a completely different space. Like, again, like, I plus and I minus have nothing in common except the 0 vector. You get one from the other by like swapping some signs, but they're still like completely different. You can't, there's nothing in common except 0. And they're both 4-dimensional each. They're 4-dimensional, and then their direct sum is 8-dimensional, which is the entire space. Okay, so this slide probably looks abstract as heck. I'm going to show you what the matrices look like, and that will make it look a lot less scary. So I'm going to look at the plus side first. Yeah, so I don't know why I put this here, but I should have put that before. I is the trivector, or the pseudoscalar. So this was a 4-dimensional space. Remember, we got duplicates. There were only 4 basis vectors, which are shown here. So we have this, and then that same thing multiplied by I, and then we have this, and then that same thing multiplied by I, because or maybe it's, yeah, because when we multiply by I, this negative I becomes a 1, and then that just becomes an xi. So this is our projected down 4-dimensional space that the P plus gave us. So what do these matrices look like? They're not that hard. They just look like this. So I'm sure the symbols look pretty scary, but the matrices are really easy. It's just 1 in the top corner, I in the top corner, 1 in the bottom corner, I in the bottom corner. So altogether, they give this is like a 4-dimensional real space, or a 2 complex dimensional space. Either one works. And right, this makes sense because P plus was this matrix, and it gave us, stuff with a 0 second column. The only difference is that this is like complex numbers here, so it's 4 real parameters or 2 complex parameters. So yeah, this is the ideal that P plus gives us. Now, I think this is the part that is really going to bring everything together. So, like I said, these two are the same, just with a factor of I, so I brought the I out. And then these two are the same, just with a factor of negative I, so I brought the negative I out here. So you could think of this as 4 real dimensional or 2 complex dimensional, where each pair makes a complex number. And it's so you could, if you want to say, well, like 4 real dimensional, you could use these 4, or if you want to say 2 complex dimensional, we can just ignore factors of I, or we could say, well, the coefficients you put in front of them can include I as well. So like, if I'm doing 4 real, then I would need to say like A plus B plus C plus D for the coefficients, but I could also do A plus BI and C plus DI if I'm allowing complex coefficients. So yeah, 4 real dimensional or 2 complex dimensional. And here's the part that's really important. These are the spin up and down spinors, which is not obvious. But I told you that spinors are members of ideals, and these are from our ideal, and these are the up and down spin states that I talked about last week. So that probably doesn't make any sense. Okay, yeah, so why didn't I put that on an earlier slide? I was trying to, anyway. Okay, so why do I say that these are the up and down states? Well, hold on. Okay, yeah, so 4 real dimensional, yeah, this is just a summary. Yeah, so these matrices are just these two. And again, you could think of, we have a complex coefficient for that basis vector, and this can be a complex coefficient for this basis vector. So in total, they kind of just give us like almost like a column spinner, a 2x1 column. That's sort of what a column spinner is. So I'm saying that these members of the ideals are spinors, up and down spin states. If you remember, the spin z operator looks like this. So let's try putting this. I'm gonna ignore the 1/2 h bar, but I'm gonna act on these spin states with the sigma z operator and see what happens. So sigma z acting on up gives us this. So if we distribute that in, this just becomes 1, which is exactly what we started with. So this acting on spin up just gives us a plus spin up. That's what the spin z operator should do. On the other hand, here, if we act on the down state, we can distribute that in. So this is zx, and this is zy, and then I've written out the full trivector here for the I. And then I think what do I do here? I've done a bunch of rearranging. So I've brought the z's together and the y's together, and I think it's an even number of swaps. So like 1, 2, 3, 4, and hold on, did I do that right? Yeah, 1, 2, 3, 4. I'm questioning myself now. Did I get the signs right?
Yeah, because you need 3 swaps for z and 1 swap for y.
Is it 1, 2, 3? Is it 3 swaps for z?
Yeah, yes, 3 for z.
Oh, what am I doing? I don't know why I wrote that there. Yeah, 3 swaps for z, and then 1 swap for y. So that's 4 swaps. So that means 4 negative signs is a plus sign. Thanks, Slava. I thought, because that sign is really important. If I got the sign wrong, then everything I've said is meaningless. And then here, I think you can put like a y in the middle, and I'm gonna work this out. So sigma z, sigma x, and then if I put y in the middle, that's fine. And then if I bring this outside, that's a negative. And then if I bring z over, and then bring x over the y, that's 3. So 3 swaps is a negative. So I'll change the sign to plus. Yeah, so this gets a plus sign. It's a lot of swapping, but it works out. So yeah, this goes to 1, that goes to 1, and this becomes an I, x, y, z. So I get this, but that is just the negative of my down state. So when I act on the down state with sigma z, I get a minus sign, which is what you would expect for the spin z operator. So yeah, basically I kept talking about ideals and projectors, and you probably had no idea why I was saying all of that. But when we take CL3 and use this plus projector and the minus projector, or actually was this? Yeah, this was just the plus projector. We got 2 complex dimensional space, and the basis vectors are up and down. These are the full. This is what up and down look like in our Clifford algebra. So when I say spinors are elements of ideals, this is what I meant. You take a Clifford algebra, you project on it, and then the results is that you get an ideal where spinors live. So how is this? How do people feel?
It is somewhat surprising because I only knew the relationship between the, vaguely the relationship between the Clifford algebra and the spin representations, but this is really nice the way you put it as these projectors.
Yeah, it took me forever to find this. Like, I had to look through so many papers and textbooks. Like, I don't know why people can't just say that this is true.
Well, because, man, I don't understand why they never told me some stuff in here either. I mean, it would be so much easier to work with.
Yeah.
Just mathematically, even. Is there some form of, I mean, because maybe I'm getting ahead of myself, but this is obviously kind of like the spin 1/2 side of things. Is there a way to extend these representations for larger or, lower numbers of spin?
Probably yes. I didn't. I think I talk about like chiral spinors in space-time, but I kind of stop there. I don't go to like spin 3/2 or like spin 1.
All right. Thanks.
Yeah. Because we're almost 2 hours in, so I'll try and finish this up. Yeah. So there's actually two ideals here. There's like this ideal and like this ideal, and they're both two complex dimensional. So like spin up and down live here. I don't know what live here. These are like weirder versions of up and down. I'm still studying this, so I don't exactly know what the other ideal means. I'm still learning. But you can travel between these two ideals by doing a parity transformation. So you leave even things alone, and then odd things change sign. So when you do that, you flip the signs that will take you from one ideal to the other ideal. But again, I don't know what this ideal means. Because like spin up and down live here. I don't quite understand what that is. I'm going to have to do more research to understand what that is. Okay, so here's, again, I'm bringing everything together. So spinors are minimal ideals in CL30. And then we already learned rotations can be done with the spin group, which also lives in CL30. Like this is SU2. So basically what's neat with Clifford Algebras is that both the spinors here and the rotations, which are SU2, they live inside the same algebra. So normally, like you think of like, oh, a vector and a matrix, those are like two completely different things, right? Like they're different. But spinors and rotations live inside the same algebra together. They like live side by side, which is interesting. Yeah, so I was going to show the chiral spinors next in space-time, CL13, but are there questions before I do? We're like almost at the end, I promise.
Would you get the same spinors if you, instead of were left doing it as a left ideal, also from a right ideal?
Yeah, so where you are right now is like basically the level I'm at. I have lots of questions still. I know that there's 4 types of spinors, so this is jumping ahead. There's 4 types of spinors. There's like a covariant spinor. There's contravariant spinors. There's covariant dotted or like covariant conjugated spinors. I wish Joe was here because he could probably tell us. And then there's contravariant dotted spinors. So I'm thinking there's 4 ideals that we have, right? There's like this one, and then this one, and then this one. I'm wondering if these 4 ideals correspond to the 4 types of spinors, but like I don't even know what the next sentence I would say after that is. I still need to do more research and learn more, because I don't understand this yet. I'm sorry, that's kind of a non-answer, but I honestly don't know what to tell you.
Yeah, it's hard to tell right now.
Yeah, but the fact that there's 4 things here and 4 types of spinors is kind of making me think that they're somehow related. I just don't know how yet. So I'm going to kind of show the same thing, and this is like the spacetime algebra with complex coefficients. Sometimes it's called the Dirac algebra. This time the pseudo-scalar is gamma 0, gamma 1, gamma 2, gamma 3. And yeah, that squares to -1. And we define the fifth gamma matrix as, this is like the complex I living in C. And that capital I is this. So together they get this. Oh, yeah, gamma 5 squares to +1. And remember, when things square to +1, we can make projectors out of them. So yeah, this almost looks exactly like our sigma z projector. We've just put gamma 5 in here instead, and like the proof is the exact same. Like we get 2 of each, the 2's cancel with the quarter, so it's a projector. Yeah, and then its orthogonal projector is this left one. And again, anything that lives in the space-time algebra, we can get a left part, a left chiral part, and a right chiral part. You know, just like we had a plus and a minus part in our CL30, we can get a left and a right part of our elements of space-time algebra. And you can add the left and right chiral parts back together to get the original thing that you have. Yeah, so these are our 2 projectors. They add to 1. And again, just like before, they split the Dirac algebra into 2 ideals. And these are like and again, vectors don't live in the ideals, they live in the direct sum. So you can take a vector gamma mu, project out the left and right chiral parts of it, and then you can add the chiral parts back together, and then you just get your original vector back. So almost the exact same thing, except I've replaced the algebra with CL13, and I've replaced sigma z with gamma 5, but the idea is the exact same thing. I tried to write out, so this is all PL. This is a 16-dimensional space, so there's a lot more work to do. But basically, when you project down, you get from a 16 complex dimensional space to like an 8 complex dimensional space. I think there's some repetitions, so like this and this are the same, I think up to a factor of -I. And I think this and this are the same up to a factor of -I. So even though there's 16 basis vectors here, you get repetitions, so you only end up with an 8 complex dimensional space when you use the left chiral projector. Oh, why do I have that slide here? Anyway, I think this is kind of why I wish Joe was here, because he could probably offer some insight into like the left chirality and right chirality of the spinors in space-time, but this is basically how you get them. You use these projectors.
Actually, I wanted to say that in chapter 11 of Road to Reality, at the end of 11.5, Penrose actually talks about those things, like the chirality spinors, which are actually called reduced spinors, or half spinors, or semi-spinors. And he says that actually the decomposition of a spinor in the higher dimensional space into semi-spinors is possible only for even dimensional spaces. So where you have p plus q equals n as an even number. So it's really interesting for me what are those projectors mean in the odd dimensional spaces like we have seen before in 3.0, for example.
Yeah, well, in 3.0 we get like, I guess you call it a polyspinor. I don't know what the word is. It's like the standard up and down spinors with 2 complex components. In the Dirac, like normally we would have if you remember, we had like a 4 complex column vector in our Dirac equation. You can basically spin it up, or split it up into like 2 parts like this.
Yes, so you will have 8-dimensional thing.
Yeah, well, it's I'm just trying to think, because the entire space is 16 complex dimensional, and when you break it up, yeah, I'm not sure, because these ideals are 8 complex dimensional each. So I'm not sure how this relates back to this.
Yeah, so what I know, we kind of have the ability to split the Dirac spinor into 2 smaller spinors, like 2-dimensional ones. You can think about them as like Pauli or Weyl spinors, and that I think will be done in some similar fashion, where you will have a projector and apply.
Yeah, well, I think these are the projectors that split them up into the 2 smaller ones, PL and PR. I think that's literally what PL and PR do. They split it into the left chiral and right chiral parts. And
it's actually it's actually very intuitive to see the helicity then as the projectors on the total spin state, right? If I'm not incorrect, or like visually you could see them as because you previously explained the projectors could be somewhat seen as the actual projections of vectors. I was thinking, if you can see the gamma matrices as vectors of the Clifford set elements of the Clifford algebra, wouldn't it be also reasonable to see the spinors themselves as some forms of geometric elements and the respective chiralities as being projected directly onto these elements, mathematically speaking, at least?
Yeah, like I'm not great at physics. I still don't even really know what chirality is. As I said, this is like a very math-based presentation. And I'm kind of hitting the threshold of what my knowledge is, and I don't know what comes next. I'm not sure how to like physically interpret this, because I don't fully understand what chirality is.
Right. Oh, that's fine.
Yeah, I think that I will try to understand over the period of the next week, why do you have those odd elements here? So, like, in my theory, if spinors are even elements, then those odd elements should be absent from the representation. And it's interesting how to relate those.
I think your definition of spinor is the spin group. Like, and I don't know why Hestenes has this definition, but, like, it seems like his definition of spinor is like this. The spin group stuff, the even graded elements. Where, and I don't know if he includes the unit norm condition or not. He might allow
he includes unit norm only for the spin groups, but spinors have like any norm.
Okay, yeah. So like I don't understand his definition, because like this definition, the ideals definition, I get things I've seen in physics like spin up and spin down. I get left chirality, right chirality. So this seems like a good definition for physics purposes, but this whole idea of spinors being like even graded elements of a Clifford algebra, I don't get that one. I don't understand the relationship. I'm not saying it's like wrong. I just don't understand why there's the 2 definitions.
In particular, I've haphazardly in the last 5 minutes through a little visual intuition thing, a drawing of how the spinors were introduced to me in Clifford algebra. And can I share my screen? Is that a?
Sure. I'm done, so I can stop sharing my screen and you can share yours. I will.
It's really quick. It's dirty work on my part. It's just a quick mathematical, just really elementary stuff. Not even matrices are involved. It's just how I understood spinors the first time because of their product. Can you see this over here?
Screen is still loading for me.
Yeah, I gave an example of what I meant by the product of 2 vectors is a spinor. That if you take 2 vectors over here, right? So one given by both given by the same basis vectors.
AirBB, do you hear me?
Yeah.
Yeah, I just can't see your screen. Maybe you can send a picture to the channel, because for some reason it's not loading for me.
Let me try. There's a bug sometimes. Maybe it's working now?
Sorry, yeah, it's still loading for me. I was looking at the wrong thing.
And for me now it's still, I see
Maybe
it.
I see it. I see like Photoshop at the bottom.
Yeah, here it is. Yeah, okay, yeah, I quickly made this. It's very rough and not at all, professional, but it still is the explanation of what I meant by the product of two vectors being a spinor. If you were to take two basis vectors, E1, E2, and construct a few vectors with those basis vectors, the product of them is quite simple algebraically to demonstrate it's equal to this, right? So this is just distributive multiplication. Is that how you call it? You just distributively multiply each basis vector and each bivector onto itself. Now, so intuitively, this is just basis vector times itself, which is equal to the identity, right? So this is just equal to 1. And it's scaled by some scalar. And these are the two bivectors. They have opposite orientations. And they're both, so you can call them basis planes for all intents and purposes. And they're both scaled too. And the idea is that multiplying, simplifying this out algebraically just yields this, right? So this is just equal to a scalar, which is equal to the scalars of the basis vectors to form the original vectors, times the plus the basis plane scaled by the scalars, right? So the basis plane with a larger size. And so it turns out that intuitively, like the scalar plus the scale basis plane is exactly isomorphic to a complex number. If you see the shape, the form of any general spinor, it's always of the form A plus B times the bivector, right? Times a basis bivector. So this is what a spinor is in practice, at least. They always yield this form, which you've seen by the projectors and so on and so forth. Mm-hmm. So what happens is that under this is as far as I know the original definition. So under what happens is that the E2 bivector, the bivector basis plane, is actually analogous to the imaginary number in the sense that it rotates any basis vectors or any kinds of vectors that you multiply it with, right? So that's why it's called a spinor, intuitively, right? So like this is a spinor, it's just a basis plane plus a scaled basis plane plus some scalar, which is what goes back to what Slav said. They can have any norm. They can have any norm whatsoever because they're just like any other geometrical entity. And what I meant by, and the reason they're called spinors, as I said, is because they rotate vectors, and you can showcase algebraically here that if you just have a regular spinor, which is a scaled basis plane and a scalar, and another vector, algebraically you multiply this out, and what ends up happening is that you end up with this, right? And this is just another vector. And what's interesting is that this vector is always just the original vector but rotated by some amount, because you can see here that what we end up having is that after multiplying these out, you have, this is the original vector, right? You end up having a new component, which is the spinor over here. And you can see that the E12 basis plane is multiplying the original vector, right? And what ends up happening is that because, as I said, the E12 is analogous to the imaginary number, is precisely because of this. Because when you multiply the E12 by the vector, you end up shifting the components in their respective you end up shifting the basis vector components of the vector, and so you end up rotating it by another direction. Does that make sense? Is that?
Yeah, I think the E12 is like a 90 degrees rotation.
Precisely. It's exactly like that.
To get like like 60 or 40 degrees, you need like a mixture of the original vector plus the 90-degree rotation. So that's what A and B would do. They sort of select how much of the original and how much of the 90-degree you want.
Precisely. They scale how much you rotate the vector, right? So what the amount. So this is why the spinor is called the spinor, and this is how I personally understood it before seeing your interesting definition. And I really found your definition to be very enlightening, because now it seems to make a lot of sense to me that physics uses spinors so much, because I mean this is a natural entity by itself, just the fact that it rotates vectors. But the fact that it's embedded within these representations is very interesting. And I have this little page that I borrowed. It's a very obscure page. I found it while searching here. And there's this very nice proof that is normally hidden in textbooks, which is that if you let two vectors, A and B, being given by their respective components, and you multiply them out, as we know, this is just equal to the Clifford product, right? So this is just the dot product and the wedge product. But more interestingly, it's equal to R, which is the spinor. And if you multiply U by R, you end up with just the same thing again. So if you multiply U and V, the two vectors, you end up with the rotor or the spinor. And if you multiply U, right, the first vector, by the spinor, you rotate that vector in such a way that you end up with the second vector and the magnitude, the direction of the magnitude of the first vector, which is what I try to draw here. You have the projection. There's a better drawing here. You have the projection of the vector. You rotate a vector using the spinor. Does that make sense?
Yeah, I mean, I'm still... Because, like, what you're describing, I see it says spinor on the page. I normally call that a rotor. Here it seems like rotors and spinors are the same thing. But I don't know. I'm very confused about these two definitions, because they seem to have almost nothing to do with each other.
Yeah, so...
I see what you're kind of... Yeah.
No, continue.
Well, I was just going to say, I see what you're kind of saying, because a lot of the spinors I had on my slides had the form of something plus I times something. So there's sort of a similarity, but I'm still confused about the exact relationship.
Well, I mean, this example in three-dimensional space over here, where you have the trivectors, I think makes it a little more clear. For me, myself, it's not extremely clear. I'm going to be honest, I still... ignorance on the topic, being fair. It's just that I think that if you look at these tables over here and so on and so forth, it to me it sounds quite reasonable that the projections and so on would be the spinors. Again, as you said, the rotor and the spinor in this section are used interchangeably. And I don't know how much that applies to the general case, right? Because there's a whole section over here about using paravectors instead of just regular vectors in the spacetime algebra, right? Because you need the time and the space components, so you just describe things in terms of the paravector. And then you end up with the spinors and so on. But I don't know how to get from this to what you showed us. But this is just how I understood it before your presentation. Of course, they have a lot to study, because it clearly is more than what appears to the naked eye.
Could you please share a link to that Wikibooks page?
Yeah, sure.
I'd also say that I once had a physics description of chirality, and to me it seemed like it was just a definition of how to break symmetry. And so you take your hands, your left hand and your right hand, and point your fingers in three orthogonal directions. And your left hand and your right hand points that last finger inside a different direction. And that's the different chiralities.
Yeah, so it
Does that make sense?
Yeah, so basically it's like a mirror symmetry.
A way of breaking the two symmetries of... But that's a very...
It's so confusing.
Yeah, well, because like when I was showing to get between the two ideals, I'm trying to remember now, because like when you did a parity inversion, you went from one ideal to the other. A parity inversion is like a mirror reflection, where you send all the basis vectors to their negatives. So
Yeah.
maybe that is related to it.
It's
different. What do the spinors have, right? Does that make sense?
Yeah.
Anyway, we've been at this for 2.5 hours, so I might end my recording. I don't know if there's more people want to talk about.
Well, I mean, just on a few notes before we end up with this, wrap this up. I like to mention that Penrose, with his whole twistor space thing, had some notes on spinors that I didn't understand at the time, but we could look at them again later after the recording and so on, and try to understand them, because I think that we're, as you said, Chris, there's these seemingly clashing definitions and these interpretations of the same thing, but obviously they're the same underlying phenomena. But it's just, to me personally, it's not clear how they're both related so intrinsically. So maybe looking at those notes, and also Gravitation by Kip Thorne and Misner and Wheeler, it has a lot of great content in spinors. There's Naber, Geometry of Minkowski Spacetime, which has a section on the spin group. I haven't read the book, but apparently it's one of the best introductions for understanding spin and spinors and other such kinds of things in the regular physical way of seeing that.
Yeah, talking about the sources, Chris, do you have a source where you have found that minimal ideals approach? Maybe you have some book or presentation or paper.
Yeah, so one of the biggest problems I've found is that there's tons of sources that say minimal ideals, but there's only one source I've found that even gets close to the slides I gave. I sent it to Joe earlier. I will dig it up. It's a thesis someone wrote.
Yeah,
but
please
yeah,
send,
like there's
because,
a lot of
I think it will help me to get into touch of those different representations.
Yeah, there's a lot of people who say, yeah, spinors are minimal left ideals, but they don't really talk about, like, when people give me an abstract definition, but they don't like give me examples, it's like really hard for me to understand. And there's just a ton of people who give these abstract definitions but don't show what I was trying to show. So I feel like a lot of textbooks are like next to useless for my level of math understanding because they don't explain things. But I'm trying to I'm looking through my history with Joe to get that thesis I was talking about.
Yeah, I understand your frustration.
Well, productive section, fellas. Lots of food for thought, I think. This is my first time coming here, by the way. Pretty good overall, I think.
Yeah, thank you for attending today.
Let's see what else we have here. So, does anyone have anything more to discuss, or is just?
I feel pretty tired already, so
yeah.
So how do we continue next time? We have some sections still left.
Alright.
If Chris doesn't object, we can just continue with his presentation just to finish it.